In this lesson, we're going to give a brief introduction to probability. Now, what is a random experiment? A random experiment is an experiment that you don't know the outcome to. For example, when we roll a die 3 times or toss a fair coin or pick a certain number of cards out of a deck of cards. Now, these are examples of random experiments because we don't know what their outcome is. However, every random experiment has a sample space, which consists of all the possible outcomes of that experiment. For example, if we are tossing a fair coin twice, for the first toss, we could end up with a head or a tail. So these are the two possibilities for the first toss. As for the second toss, if I had a head on the first, I would still have the possibility of having a head or a tail on the second. Similarly, if I had a tail on the first, I would still have the possibility of having a head or a tail on the second. So the possible outcomes are a head, then a head then a tail then a head, and a tail then a tail. So the sample space of the random experiment that we call U has all 4 outcomes of the experiment listed as ordered pairs, when the first element corresponds to the first toss and the second element to the second toss. And we define n of U as the cardinal of the sample space, which is the number of elements of U, which in this case is 4. Now, what is an event of a random experiment? That is a subset of the sample space. Going back to our example consisting of tossing a coin twice with that given sample space U, we consider the event consisting of obtaining at least one head. So going back to the sample space, these are the outcomes containing at least one head. So these outcomes form event A, which is a subset of U, and the cardinal of A is 3 as it contains 3 elements. As to find the probability of an event, that consists of finding the chance of occurrence of an event. In our example, the probability of A is 3 out of 4, as 3 outcomes of the total 4 outcomes form event A. Therefore, to find the probability of an event, we divide its cardinal by the total number of outcomes. Now let's discuss some probability properties. Given a sample space U of a random experiment, we consider an event A of that random experiment, which is a subset of U. As A is a subset of U, its cardinal is smaller than the cardinal of U. Therefore, the probability of an event is a number between 0 and 1. It's positive as we're counting elements, so that cannot be negative, and smaller than 1 since A has less elements than U. Now, what is a certain event? A certain event is equal to the sample space, like when that event will definitely happen, and its probability will be equal to 1. For example, if the world population is the sample space and I define an event consisting of people aged less than 200, that event is certain as every living human being is definitely aged less than 200 years. While impossible events are those that are equal to the empty set, as they cannot possibly happen, and their probability would be equal to 0. For example, going back to considering the world population as the sample space, the event consisting of people aged more than 200 years is impossible and has a probability of 0. Now, what is an opposite event? If we define the event opposite to A by A prime would consist of the remaining elements of U outside of A. Going back to our example where we tossed a fair coin twice with that sample space U, we had the event A consisting of obtaining at least one head with a probability of 3 out of 4. Now, its opposite event A prime would consist of obtaining no heads. only including the outcome with 2 tails with a probability of 1 out of 4. Then the probability of A prime is 1 minus the probability of A. And that is because the number of elements of A with that of A prime form the entire sample space U. Dividing all terms by the cardinal of U, we end up with the probability of A plus the probability of A prime equal to the probability of U. And U being at the sample space, its probability is 1. Solving for the probability of A prime, we end up with P of A prime equal to 1 minus the probability of A. Now, given another event B, their intersection would form the event A and B, which consists of the outcomes common to both A and B. And 2 events are mutually exclusive, or what we also call incompatible events. It's when their intersection is actually empty. It's when the 2 events are represented by sets that are disjoint with no intersection. However, the union of 2 events consisting of the elements in A or B, so the elements could be in A only, B only, or in both A and B at the same time. The probability of A union B, consisting of everything inside A or B or their intersection, would actually be the probability of A plus the probability of B, but notice that the intersection was taken twice by adding the probabilities of A and B. Then we have to subtract the probability of the intersection to consider it only once. But if A and B are incompatible with an empty intersection, then the probability of the union would exactly be the probability of A plus the probability of B. Now, for example, if we consider the random experiment consisting of rolling a fair die once, and by fair we mean that the die is not tricked and all faces have the same chance of occurrence. Now, the sample space U would have 6 outcomes consisting of the 6 faces of the die numbered from 1 to 6. Now, considering the event A, which is obtaining an even number, event A would include the possible outcomes 2, 4, and 6. And the probability of A would then be 3 out of 6, which is equivalent to half, as event A includes 3 elements out of the total 6 outcomes. Now, defining event B as obtaining a factor of 6. Event B would then include the possible outcomes 1, 2, 3, and 6, and the probability of B would then be 4 out of 6, which is equivalent to 2/3, as 4 out of the 6 outcomes form event B. Now, the intersection of A and B includes the outcomes 2 and 6. Then the probability of A inter B would then be 2 out of 6, which is equivalent to 1/3. And the probability of the union of A and B, being the probability of A plus the probability of B minus the probability of the intersection, would result in having the probability of A union B equals to half plus 2/3 minus 1/3, which is equal to 5 out of 6. And that actually could be confirmed by the Venn diagram, as we notice that 5 out of the 6 elements are in the union of the 2 sets.